Okay, cool. So thank you for coming. Maybe more people will come, I'm not sure. But we can go ahead. Yeah, so I have some announcements. Today we were supposed to have a guest lecturer, but he was sick, so I hope he will be well enough to come present online next week. So that will be next Tuesday, and then the report will be the Tuesday after that. And originally that Tuesday was for presentation slots, but only one group had signed up in that slot anyway, so I just moved them around. And also next Thursday, originally there's supposed to be a guest, but there's also a conflict, but I will fill in. So there will be some report and I'll talk about filters. So we talked a little bit about filters like a long time ago, but I'll talk some more about it. And then so now that originally the slide deadline was this Tuesday, because that was the first presentation, but now the first presentation is this Wednesday at 1:30, or next Wednesday at 1:30. So the slide deadline is now starting in the first presentation slot at 1:30 on Wednesday. And I think everybody here has already done it, but we sign up for the presentation slot if you have not done it. And this is just a reminder, the extra credit is due May 1st. The final project is due May 2nd. Okay, cool. So today will be synchronization without locks. And we did with locks back when we were talking about parallel programming. But today I'll talk about memory models and how you can do synchronization using parallel primitives. Okay. So the first thing that I will talk about is sequential consistency, which is it's a memory model for how you think about the ordering of instructions in your program. And in general, these memory models are they're rules on guarantees that you can get when you get instructions. And I'll explain what it exactly means later. Yeah, so like I said, a memory model defines the rules under which writes to stored objects become visible to later reads to that data. And the reason that we need that is it allows us to do compiler optimizations, like for example, loop fusion, which sometimes they can move statements in the program and that can affect the order of the operations to potentially shared variables. So this is an example of loop fusion for these two loops over the same space, 0 to 300, and A of I. You have two arrays, A and B, and the first one does A of I is A of I plus 3. This one is B of I plus 4. And then loop fusion is just combining those two into one loop shared. And without a memory model, the compiler cannot do optimizations like this, because if the program is multi-threaded and if these variables were shared, then you wouldn't be able to make guarantees about correctness, because for correctness, you need to be able to say you need to be able to say something like, if I write some data and then I read that data afterwards for some definition of after, then it's going to reflect what I just wrote. And without memory model and without rules in the underlying hardware, we cannot guarantee something like that. So we're going to use this motivating example a lot today. So this is a very simple code. So you start A equals B equals 0, and they have two processors, 0 and 1. And they're just doing something very easy. They have two variables, A and B are shared. And processor 0 first puts 1 into A. The move is like second thing into the first thing. So you put 1 into A, and then you put B into EBX. This is right this way. Then you have processor 1, and it's just like the reverse. You're going to put 1 into B, and you put A into EAX. Yeah, and that's just store and load. So the question is it possible that processor 0 EBX, so this thing, and processor 1 EAX over there, both contain 0 after the processors finish their code? And processor 0 and 1 are running in parallel.
A and B are two addresses.
A and B, yeah, A and B are different.
They are different, but they refer to the same address.
The A is shared between 0 and 1, and B is shared between, but A and B are separate locations.
Oh. Other one?
Why is it impossible?
Well, because if one process needs to reach that load instruction, it's have to execute that store instruction, which will override a value of A or B.
Yeah, so you're saying like by the time that anybody gets here, at least, like if we get here, then A is one, and then eventually they're gonna move A in EAX, and same thing on the other side. Yes,
But if we consider cache,
why is that?
because for example, if you keep that processor one, first execute every instruction, so that means the EAX will be 0 in it. And then we let processor 0x execute. However, maybe that processor 0 has its own cache that contains it over that B, and then you will. And at this time, it wasn't like invalidated. So, and then you perform the move, and then you will have a.
I see. So you're saying like processor 0 had some copy of B, and even though processor 1 updated B, like it was not updated for 0, and then so like you may move 0 because there's a local copy. It's a good point, actually. For the cache, like for cache coherence, the cache line would have to be invalidated when B gets updated over there. But there are some cases, not really in straight line code, but in loops, you can read the cache value. Like there's like loop hoisting, which is if you're computing something repeatedly in the loop, some compiler may like remove that thing that you're repeatedly computing because it recognizes that you're just doing the same work over and over. But in this case, we can assume that the cache coherence protocol will tell us that B has changed. So this is a good point. Like they can, in this case, if we assume that the cache coherence protocol does it for us, and we assume that the stores have to happen before the loads, then it is true that at least one of them will have to be 1 and then. But that is making the assumption that the memory model, which is that the stores, that they do happen in this order, that when you write code like this, the stores will happen before the load. And we will see later that that is not necessarily always true. So the most, I guess, one of the oldest and like most straightforward models of memory models is called sequential consistency. And this is a lot, but it says that the result of any execution is the same as the result if all of the operations were ordered in some sequential order and all of the operations of each individual processor appear in the sequence specified in the program order. So like if we think about the previous example, that's saying like the stores have to happen before the loads. And it's not saying that there is one total order that is possible. Like even in the very simple example, there's 4 instructions and you can interleave them in some different ways because they're parallel threads. So the sequence of instructions defined by the program is interleaved with the sequences from all the other processor's programs. So you can think of those different programs as providing some global linear order of all the operations happening. And the second part, or there's multiple parts, I guess. The second part is that a load instruction receives the value stored to that address by the most recent store instruction that precedes the load. So like you were saying, in the example, like the store has to happen first under sequential consistency. And the hardware can do some underlying optimizations, but to obey sequential consistency, it has to happen that loads and stores obey some global order. And so under sequential consistency, it is true that none of those things, the previous example, you will always get at least 1 in either EAX or EBX.
I heard about something like, what do you call it? Disorder execution or?
Like out of order execution? Yeah, we will go through it. We'll talk about it. Yes, but the sequential consistency, it's like, it's a model, and model, like, you know, models always have to do some abstraction, and models will never 100% like accurately reflect what is actually happening in the system. This is like some way, it's like some assumption that you make on the system, and then you use this assumption to prove things later.
So to clarify, is this stating that like all loads will happen before their corresponding stores, or is it like your code will run sequentially as you've written it?
Your code will every processor will respect the processor order. It's not like if you wrote like load store load, it will not become like load store.
I see.
It's like it will have to follow that load store load order.
That makes sense.
Good question. Okay, so let's go back to this. This is the same example that we just had, and these are, you can trust me that there are 6 possible interleavings of these 4 instructions. And we have these 2 registers, AAX and BBX, and we're going to say that sequential consistency implies that no execution ends with both of them having 0 in it. So, okay, let's do the first one. Like the easiest one is if processor 0 goes and then processor 1 goes. So what will be in EAX and BBX after we do that?
P1 and then PX.
Yes, good. Because here B was 0, so BX got 0, and then I think A was 1 at that time. But there are many possible interleavings. So what happens if we got this one? So that's 1, we put 1 into A, and then we put 1 into B. Yes. And then I guess same here, because this is 1 and 3. And same here, because this is 3 and 1. And so those are all 1 and 1. And what about this last one? So it's 3, 4.
PX. PX.
Yes. Good, exactly. Yeah, so as you said, that's making an assumption that you follow the processor order, none of them, or there are no cases where they will both be 0. But actually, in reality, no modern machines implement sequential consistency. Like you said, like they all do out of order execution. Does this make sense? Okay, so the reason that we are talking about sequential consistency is that it's the easiest way to make proofs about correctness in these parallel systems. So the reason, because we can talk about global ordering, and we can talk about like you have every processor has some list of instructions, and they get some sequential interleaving, and at the end you're trying to reason about some global interleaving of the operations. You can talk about this happens before a relationship, and that is defined by the processor order. So like in this one, this happens before this one, and this one happens before this one. And this happens before is linear. So if you have 2 instructions, either X happens before Y or Y happens before X. If they're in different processors, they this happens before, like depends on the interleaving that you got. And yeah, it has to respect the processor order, which is defined by the program, and a load, according to sequential consistency, a load from a location in memory reads the value written to it by the most recent store, according to this happens to relationship, or happens before a relationship. So that's how we were reasoning about that you have to have at least 1 in the registers. And finally, for the memory resulting from the execution to be sequentially consistent, there has to be some linear order, according to this happens before a relationship, that yields that memory state. And this is kind of like implicitly what we were doing when we were saying at least one of them has to be 1, because the stores happen before the loads, and then no matter what order the stores happened in, like at least one of them happened before the loads. So this is how you prove things using sequential consistency. Like you have a program, and then you assume this memory model, and then you say instruction X happens before instruction Y, and then therefore some other things. And we'll do more examples.
So here we're talking about load and store, which are memory operations. So I'm wondering, because we have multiple processors, so for something like pure calculation instructions like add or multiply, they can be executed concurrently.
Yes.
So that in between those instructions, we don't have a happens before.
No, right now we're just talking about load and store, but you can assume the same sequential consistency that you have to respect the memory, or you have to respect the processor order. Like if we had, like, for example, A equals A plus 1 and then store A, then you would assume that you're storing A plus 1.
Okay.
That makes sense? Like you still have to, you're assuming that the math calculations that you're doing are the result of the most recent math calculation is what you're storing if you call store after you do those.
Yes.
Yeah. So that is sequential consistency, and we are going to use it to prove how you can do mutual exclusion without locks. So we did mutual exclusion along a while ago. We were doing parallel programming, and we can remember that a critical section is a piece of code that accesses a shared data structure that must not be accessed by two or more threads at the same time. So before we were using locks to implement mutual exclusion, and most of them employ atomic read, modify, write, basically to implement a lock, like read, modify, write to implement basically like a bit to say whether or not it's in exclusive mode. And these are these special operations like exchange, test and set, compare and swap. Exchange is the most popular one, or like, actually maybe compare and swap is the most popular one, but anyway, these are all atomic operations, which means they happen as one, from the programmer's point of view, it's like one operation on the underlying data. Exchange is like, you give it like A and B and it puts B where A is, test and set, you check whether a value is something, and then you set the value. And compare and swap, we'll talk a lot about compare and swap, but compare and swap is like, you have an old value and you have a new value. And then you have some pointer. And if what is at the pointer is equal to the old value, then you replace it with the new value. And you can see like how you would implement a lock with compare and swap, because you would test if the lock is 0, and if it is, then you would swap in 1.
These are the C functions, or like?
Yeah, these are like C atomics.
I see.
I think exchange is also like in lower level assembly. I think that you probably implement compare and swap with variants of exchange. Okay. Yeah, so we had mutual exclusion, and previously we were using locks. But one question is like, do you need to do it with locks? Can you implement it with just load and store? So not like any atomic operations. And it turns out that yes, Decker and Dijkstra show that you can, as long as you have sequential consistency. And that is them. And their algorithm is kind of complicated. So I will use a simpler algorithm called Peterson's algorithm to illustrate how you do it. So let's say we just have 2 threads. We have Alice and Bob, and we have some shared variable X, and both of them want to apply some function onto X. Alice is applying foo, and Bob is applying bar. And they cannot do it they can do it at the same time, but they should not do it at the same time. Because for correctness, for mutual exclusion, you want only one of them to be accessing it at one time. And so you have some X, which is the protected variable, and we're going to use these metadata. We're going to set 2 booleans. One is called A wants and one is called B wants. And then we're also going to define this variable called turn, and turn can have 2 values, A and B. And we use these variables. We'll see how we use them, but basically we're going to use load and store to implement mutual exclusion with these variables. Okay, so how it works. So Alice and Bob are running in parallel, and these are just symmetric. So we're just gonna go through one of these first. The way this works is that Alice first sets A wants to be true. So she wants to do her function, and then she sets turn to B. And there's this empty while, which is while B wants is equal to true and turn is equal to B, then she waits. So this is saying that it's not her turn, and also that the other person wants to go. And then if both of these are true, then this thread has to wait. And if both of them are not true, or sorry, if either one of them is not true, then she can continue. Either the other person doesn't want to enter the critical section, or it is her turn to go. And then if this is sense, or if you pass through this, then you can enter the critical section, and then once you finish the critical section, then you just set A wants to be false, which is the end of this round. But if it turns out that she doesn't want to go again, then you just start again, and then you set wants to be true. So this is a relatively simple algorithm, but it's maybe not obvious why it implements mutual exclusion. And then on the other side, it's the same, but just in reverse, if you flip A and B.
It is mutual exclusion because it is essentially analogous to the first example we see then, because then like the A and B cannot both be zero, so that is why we choose.
Can you say more?
It is like the first two instructions on both sides, they are like the first two instructions we had before, and no matter how we interleave those two instructions, only one of the while loop can be zero. So that is kind of like why it is neutral.
Yes, exactly. So like in the previous example, we had like A and B and they were shared among the processors. And like if you remember the simple example, like we put one into A and then we put B into our register. And here we're basically saying this is like putting one into A and that one is putting one into B. And then you're setting the shared variable as the other thing. And yes. It's not exactly the same because in that one, you had two registers, like EAX and EBX, but then this one turn is shared. But the first part is the same. And then the second part is necessary because you need some notion of whose turn it is to continue. Because if you just had A1 for B1s, then if both of them are set to true, because both of them concurrently entered the section and started, then there would be no way to tell who was supposed to go forward. But because there's a bunch of consistency, somebody has to get here first. Either Alice has to get here first, or Bob has to get to his second line first. And then one of them is going to continue. That makes sense?
So like thought experiment to see where I'm going wrong. Let's say, so it's the first line of Alice,
Mhm.
right? So A wants is true. Then the first line of Bob, then the second line of Bob, third line of Bob, that would pass, right? And then you're in the critical section. And then in theory, then you can do Alice line 2. And then you could continue, right? If you kept doing Alice. Weren't those both get in the critical section? Or am I going wrong?
Let me try to follow what you said. So
Yeah.
A1 is true,
Yeah,
B1 is true,
yeah,
A turn is A.
Yeah.
And now we're here.
Yeah.
And Bob is staying.
yeah.
Uh,
Oh, I see. Okay, I see.
yeah, sorry, this is like an empty while.
I see.
So Bob stays here,
I see.
and then turn is A.
But because A1 is 4 is current, all right? Oh,
A1 is true.
true.
Yeah, but both of them are true. A1 is true and turn is A, because Bob said turn to be A. So Bob has to wait because the turn is A. And then eventually Alice will get to go, and then she will continue, turn goes to B. And then B wants is true and turns. Yeah. B wants is true and turns B. But one of them has to be able to continue because then turn becomes B, so the Bob will keep going. Yeah, it's a little confusing for sure. I'll do some proofs on it and maybe hopefully that can become clear. And if it's still not, then we can go back to it. Yeah, so this is the algorithm. And the intuition is that if both of them try to enter through the critical section, then this is kind of what you're getting at. Like whoever is the last one to update turn has to spin and the other one will progress, because then like turn is equal to whatever they just set it to, and then they can't continue. And if only Alice wants to enter the critical section, then if only Alice tries to enter the critical section, then she will continue because we want to set the false. Because if Bob just didn't execute, then Alice will just keep going. And similar on the other side, like if only Bob is running, then Bob can just keep going. And that is an important property. This is the reason, like you could implement mutual exclusion by just like having turn, I guess, and then both of them would set turn. But the reason that you want A1 and B1 is that if one of them is not running, then But like if it was Alice's turn and Alice doesn't want it, but Bob does, like Bob has to wait, even though there's no reason that technically he should wait. So that's why you need both wants and turn. Okay, so that is some intuition, but we want to be more concrete about it. And we're going to prove this theorem that Peterson's algorithm achieves mutual exclusion on the critical section. And we will prove it with contradiction. So assume for the purposes of contradiction that both Alice and Bob are in the critical section together. And consider, and we need to consider just like the most recent round of doing this algorithm. Like it doesn't matter what happened in previous rounds. So we just consider the most recent time each of them is going through this critical section. And we're going to find some contradiction. So this is the algorithm. And the way this works is with sequential consistency, the way that the proofs work is that you find like chains of operations using happens before, and then you like compose the chains, and then you try to prove something about them. So the first step is without loss of generality, assume that Bob was the last one to write the turn. And it doesn't matter because you can just reverse this argument. But okay, so that means that Alice had to write turn before Bob wrote the turn. That's just the assumption. And so A wrote happens before B wrote to turn. One of them has to go first. And this is Alice's program order. So this is just the order of her instructions. A wants equals true happens before turn is set on the side. And then Bob's program order is the same. But it's, I guess one common thing is that, of course, this writing to turn happens before this while. But in this while, there are two reads. You have to read A once and you have to read turn. And because like evaluation happens left to right. So of course, turn happens first, but that happens before this read of A once. And that happens before read of turn. Like you turn, you write there, and then you read, and then you read. And now you can see like this is overlapping with this because happens before is linear. So like this happens before this, which is equal to this, which now happens before this. So you could like concatenate these chains. And then the same here, this and this is the same. So you concatenate this chain after this chain. So now you can combine them all. And yeah, so if we combine them all, we can make some argument about what the values of the things were. So this happens first. A once is true. So A once is true happens before this one, happens before this one, happens before these two. So what was A once? Is true. Yeah. And what about turn?
A.
Turns A. Yeah. Exactly. So that is what we got because we composed these chains. And this is a contradiction because in the beginning we said that both of them got to the critical section, but we showed that that's not possible because if these values were the way that they are, then B should not have continued. Yeah, and that's how you prove things with sequential consistency. And so like, yeah, like I said, like you just compose, you make some linear ordering of the instructions and you compose the ordering into some like instruction order. And then you go backwards and you try to reason about what the value must have been. That makes sense? Cool. But of course, like I said, machines nowadays don't implement sequential consistency, so they actually implement something called relaxed memory consistency. The hardware reorders the instructions, and also the compiler may reorder the instructions. So that's not to say like sequential consistency is bad or anything, like it is a valuable tool and it is maybe the only way that, one of the only ways that we know how to prove things in this vein. So it is still a useful thing to do. And it's not totally wrong. Like we used to have machines that implement sequential consistency, but nowadays it became less popular. So suppose that we have this is the same that we had before. We have move 1 into A and we have move B into this register. Or sorry, this is load. And suppose that we like one possible reordering, I mean, the only possible reordering of these instructions is that you put the load before the store. Why might the hardware decide to reorder those instructions? On one processor, there's nothing wrong with reordering them. You only cause some issue when you have multiple processors. But even on one processor, the hardware might choose to do this reordering to cover the latency, because the store, like once you issue the store, you kind of like, you don't necessarily have to like wait for it to continue your program. If you're not using the value of A immediately, like if you're just loading, this is storing 1 into A, which is some value in memory. And if you're not using, like this is not using A for the rest of the program. And so, but you may use B later on in the program, but there's some load latency. So the faster that you can issue the load, the faster you get the value. And so to cover the low latency and get instruction level parallelism, the machine might choose to do hardware instruction reordering. When is it safe for the hardware compiler to do the reordering? If A is not equal to B, so like you were saying, if they're equal, then you cannot reorder them because you need to wait for the store to finish before you get the load for the correct value. And also when there's no concurrency. Because if there was,
Just kind of make sure that restart instruction has finished.
you cannot. You cannot, but I will tell you later that the hardware takes care of it for you. Yeah. Good question. For the purposes of like the programmer's view, the store finishes. You don't need to wait for the store to finish before continuing, even if you need the later value, but the load needs to, the low latency for memory needs to finish because like you're fetching something from memory. I'll tell you how they kind of like hack around it. Immediately, I guess. Okay, so this is the simplified model of the hardware system. You have the memory system, you have the processor, and you have the network through which they communicate. Processor stores things into the memory system and loads things from the memory system. And yeah, so the way it works is that the processor, like this processor can issue instructions in general, and including stores faster than the network can handle them, because the network is like bound by memory latency. So, but because the program may not require you, like if you're not immediately using the results of the store afterwards, you don't need, the program doesn't need to finish the store to keep going for correctness' sake. And so there's a store buffer that can buffer the instructions, and if the processor is issuing like a lot of stores, it can just put them in the buffer and keep going with whatever it needs to do. And then the network can eventually flush this buffer down into memory.
Here we're talking about the network or the communication.
This is the communication between the processor and the memory, like the bus or something. Yeah. Yeah, you can put them in the store buffer, and then the processor does not have to be bottlenecked by store latency.
I mean, I don't have a modern understanding of computer architecture, but I thought this issue was resolved from like pipelining, right?
Mhm.
Or am I
Is this issue resolved with pipelining?
like with like issuing stores slower than the memory system can handle it.
Mhm.
I thought like pipelining hides that issue. I guess not.
It hides it for instruction latency, but it does, maybe it does not necessarily hide it for, like, if in the pipeline you want, if you issue store A, and then while store A is in the pipeline, you issue load A, you need to get what you, like, for any kind of consistency, you need to get what you just stored, even though it may not have been fully propagated to memory.
Nice.
So either the pipeline maybe can allow for you to do that, or you can read it from the buffer.
That makes sense.
But it's a good point that pipelining can hide some of the latency, but pipelining does not necessarily hide the memory latency, I guess. It can hide like the, I guess, like the, the cycle of like the instruction latency.
Okay.
Yeah, good, really good point though. So there's the store buffer because you don't have to wait for this. You don't, if the program doesn't need to wait for the stores, then it should not have to wait for the stores. So it can just buffer them and the network can deal with them eventually. And there's load, and then the program may have some loads. And because the loads will definitely have to stall until it's satisfied by doing the memory fetch, the loads have priority and they can bypass the store buffer and immediately try to fetch the thing from memory because the machine is trying to hide that latency.
So we have a buffer in our previous model, the memory consistency sequential.
I guess for consistency, like for sequential consistency, the actual hardware is hidden. Like the assumption that we're making of like you have to follow the processor order is not, it doesn't assume that you have any specific hardware, but it just, sequential consistency is like some assumption on the hardware that's like, if the hardware is sequentially consistent, the programs will follow the program order. But this is like what your hardware, this is like what hardware in multi-cores often looks like. So you can see like the loads may bypass the stores, and this is how you get the out of order execution. Because if the load and store are not dependent, then like there's no reason that the load should have to wait. And yeah, so this hack of having the store buffer, it works, but then you have this issue, like I was saying, if you are trying to load something that you just recently stored that has not yet finished flushing down to memory, then it needs to check the store buffer first for the most recent value that was written down. And it can either be in the store buffer or maybe it's not, and then you just get it from the memory system. And therefore, the load can bypass the store to the different address. And with this kind of hardware, you do not necessarily get sequential consistency because even though you may have issued like load then store, from the point of view of the machine, the load may complete first. Or from the point of view of even you get the result of the load first before the store completes. Yeah, so this is like, it's a little bit hard to reason about because like looking at this, you may wonder like, how is anything even ever correct? It's like if the loads and the stores can just happen in any order, and you have no guarantee on like what actually you're getting back. Like it really seems hard to write correct programs, and it is. But at least that's like what relaxed memory consistency is. Like we have some rules on consistency that are not necessarily as strong as sequential consistency. So for example, one popular one is called x86 total store order. And there's like, they have a lot of rules. And they have some that you might, some that seem natural, which are like, loads are not reordered with loads and stores are not reordered with stores. Stores are not reordered with stores. So this is some example instruction trace that you might have. So you have like store 1, store 2, load 1, load 2, store 3, before load 3, load 4, load 5. So like you have some interleaved loads and stores, and because loads cannot be reordered with other loads, like you could not put load 5 before load 4. And because stores cannot be reordered with other stores, like store 1 cannot become before, or sorry, store 2 cannot become before store 1. But oh yeah, and stores cannot be reordered with prior loads. So the store 3 cannot be swapped with this load 2. But A load can be reordered with a prior store to a different location. So this is what we were just saying, like because of the store buffer, the load may do the load bypass, and it can be reordered with a prior store to a different location, but not to the store to the same location. So you still do, like if you store A and you load A under this total store order, you're still reading the A that you just wrote down. So like you're getting the value that you expect to get. And there's some other stuff going on, like loads and stores are not reordered with locks. Stores to the same location have to respect the global order. So this is kind of like a corollary of this one. You cannot reorder instructions to the same location. Or you cannot reorder loads and stores to the same location, which means that they have to respect some global order. And locks also respect the global order. And then memory ordering preserves causality. And yeah, so like I said, total store ordering is weaker than sequential consistency because loads can be like you don't necessarily have to follow the program order, and loads can move up in this ordering. Okay, so what does that mean for what we were just doing? So we have this example again. Put 1 into A, put B into EBX, put 1 into B, and put A into EAX. And so now, can we end up with 0, 0 in EAX and EBX? How can we get that?
Because if those loads instructions get executed first then store.
Yes, exactly. Yes, so like if these got reordered, like 2 and 1 were reordered, and here 3 and 4 were swapped as well. Now this, if we got like 2, 4, 1, 3, then both of them would end up with both EAX and EBX end up with 0. And so like I was saying, instruction reordering violates sequential consistency. So you may not get the orderings that you expect. This Peterson's algorithm that we were just doing. Can reordering cause issues in the proofs that we were just doing for Peterson's algorithm?
We cannot reorder from that x86. We cannot reorder we cannot reorder a load and store if they write to the same location. And here we both write to turn and read function.
Yes, I see. You're saying we write the turn and we read from turn, and turn, like this turn is not going to flip from the order. True.
Maybe in this if we write in this order, we will read B1s first. But if we read turn first, we swap the B1s and turn.
Yes, good point. Yeah, because I think maybe if you're saying like I think turn is fine because like this store was going to happen before this load, but there is some issue in B1s because B1s may be reordered. And even if I'm not sure, does it solve it if you flip B1s after turn, like if you switch the order of these? I'm not sure actually. I don't think so. Because
Yeah, I think it does. Because if you were doing total ordering, then because for let's just take box and B1 equals 2 and turn equals to A, there are two stores, so you cannot reorder those. And then the next instruction is turn equals to A. That is a load instruction. However, it cannot be reordered with turn is A because that is a store into the same location. So that's kind of synchronized.
I see. So you're saying like if turn turn equals B was here, then, I mean, even when turn was here, you still cannot reorder this store and this load.
Yes, but currently the issue is that, so for example, if, let's use Bob again, so basically, the first two instructions are store, that's true, but the third instruction is to load A1, so that means we can, theoretically, we can just execute load A1 without doing any of those store. And
Exactly.
similar goes for others, and we can load P1s without doing any of those store. So in both cases, both while loop just structure, and then we all enter the critical section.
Yes, exactly. Yes, so this is you said, if B wants and on the other side A wants gets reordered before the stores, or sorry. Yeah, before the stores, then both of them would enter the critical section. So we have to do something to fix it. And the way we're going to do it is through something called memory fences. And memory fences are these programming constructs, and they're a thing that the programmer can call down into the hardware that forces some ordering constraint between the instructions before and after the fence. And this is an explicit instruction that you can issue, like in x86, you can write mfence, and then the things before the fence have to happen before. The things before the fence have to happen before the things after the fence. But memory fence can also be implicitly issued by lock, exchange, or other synchronization. And in C++, there's also, you can call memory fence using this atomic thread fence. There's some documentation, and the cost of the memory fence is comparable to like an L2 access. So I think people are trying to get this better.
So here we're only talking about 1 second. So that means the instruction on this single thread must conform to the fences.
Yes, so in the case of like Alice and Bob, you'd have to put it in both Alice and Bob's code. Yeah, so this is what we had before, and we have to insert it both here and here. And so that's one way that we can restore the sequential consistency using the memory fences. And that fixes the issue of the hardware reordering, but sometimes sometimes the fence is not enough because the compiler can also do reordering. And the way that the compiler can do reordering is it's a bit complicated. So I guess you were kind of saying this in the beginning, like the compiler can cache some values through loop hoisting. And so like if it hoists B once or turn, then it may be reading the old value, even though it has changed elsewhere. And so to make sure that doesn't happen, you have to read the variables from memory always. And you can do that by declaring the variable as volatile. So the compiler doesn't optimize away those references by just reading some local copy. And this volatile keyword tells the compiler that the variable has to be reread from memory every time it is used, instead of optimizing the memory access out or caching the thing in the register. And this is like the assembly for declaring volatile, though I think in C++, you just say like volatile int something or volatile float something, and that would just work. Okay. And in C11, there's special atomic store and atomic load instructions that you can use. So you can define this memory model with these atomic stores, which you declare the variable using atomic, and then you use atomic load and atomic store to enforce the consistency of the instructions. So this is just the example for Alex. These are both stores. They become atomic store, which takes the address of the variable and the value that you want to store. Atomic load just takes the thing of the address of the thing you're trying to load and reads it, and that restores the consistency. And there's a lot of nice theory about these things. One maybe sad one is that any n-thread deadlock-free mutual exclusion algorithm using only load and store memory operations requires omega n of space. So this thing, like using turn and A wants and B wants, scales poorly with the number of threads. So that is a little sad, but it is nice. It is still a nice theory, it's a nice algorithm. And also if there's this, and yeah, and also these deadlock-free mutual exclusion algorithms, because there's no sequential consistency these days, you have to use a memory fence or atomic compare and swap. You have to use this synchronization barrier. And therefore, it is useful for hardware designers to implement these special operations like compare and swap and exchange to support atomicity, because this grows with the number of threads. Does that make sense? Are there questions? Okay, let's keep going. I promised that we would talk about compare and swap. So compare and swap is this key operation for lock-free algorithms. We have load and store like we did before, and compare and swap is, you can build, I think like every lock-free data structure I know uses compare and swap. So it is a key tool that people use. And it is implemented using this CNP exchange instruction in x86. And C provides this atomic compare exchange strong, which works on integers only. So it is slightly annoying that it doesn't work for floats, but it just works on integers. It is what it is. And this is the API. So compare and swap is CAS, C-A-S, and it has these three things. It takes in this pointer, like the type is T. T is an int, either 32 or 64. Takes in a pointer to X. It takes in a value old and it takes in a value new. And it does this whole thing atomically, which is it checks if you reference X, it checks if this value is equal, checks if X is equal to old, and if it is, then it says X equal to new and return true. Otherwise it does nothing and returns false. And yeah, so this whole thing executes atomically, and it has there's this implicit memory fence inside to do the synchronization. Okay. So how can we implement a mutex using CAS? We can implement a lock directly. I was kind of saying something like this earlier, and this is like the proof that you can implement a lock using CAS in just theta 1 space. The proof is, I guess, this 2 lines of code. You have this int, which is the lock, and to lock it, we spin, and false means that it is unset, and true means that it is set. And we finish this lock function when we have grabbed the lock. And the way it works is that you keep spinning in CAS on the lock variable, and if it is false, you try to set it to true. And if this returns true, then we exit the while and we have grabbed the lock. And if it returns false, then we keep spinning because the CAS returned false. And on the other side, unlock is much easier. We can just directly set it to false. You don't have to do any CAS or anything. Because if you have grabbed it, then you have exclusive access on it. Does this make sense? Okay, so we have come, this is like I think we had this exact problem when we were first doing multi-threading, but this is just, you want to add numbers into an array. This is an array of size 1,000,000. We have some array of this size, and we want to add up all the numbers in, we want to reduce all the numbers in the array into result and do some compute on it. Compute is just some arithmetic. And at the end, we can print the answer. And we can see that there is an issue because you can't just stick this parallel 4 on it because it will cause a race on result, because you need to protect the variable somehow. So how could you protect it using locks? It doesn't have to be efficient. Like if you had a lock, how would you make sure that result was correct?
Whenever you want to write the result, you need to acquire the mark, and after the write,
Good, exactly. Just making sure. We keep the parallel 4 as it was, and right before you add, you lock it, and then after you add, you unlock it. And here, this example has pulled compute outside the lock, so it stores it in temp. why might it do something like that? Or like, can you think of a reason why, like before compute was here, and that's not wrong.
We can parallel.
Yes, exactly. Yeah, you don't have to wait to get the lock to do the compute. And if you want to grab the lock for as short time as possible.
If we just do this rhythm, just the signature system comes.
Yes, exactly. Mhm. Good. Okay, and this is correct, but one issue is what happens if the operating system, like the threads are scheduled, what happens if your thread, you grab the lock and then it swaps your thread out right in this loop iteration after it acquires the lock. Can the other threads continue? Good. Yes, all the other threads have to wait because you have the lock, now nobody else can continue. And ideally, we don't want to have to do that. So instead, and if you just look at what we're doing, all that is happening is that we are loading X, which is result, you're adding temp, and then we're storing it back. So how can we use CAS to implement this? Yes, so like result is an X, and then what is an old?
It should be the result you have from the previous iteration. It's the old value of the result.
Yes, and you?
It's the new result you calculate.
Yes, good, exactly. So we can do this compute like we just did before. This outer for loop is in parallel, and we have this do while old is equal to result. New is equal to old plus temp, where temp is the thing that we computed, like this is the thing that we want to add. So, and then we do this while. On the while, this is the same idea as the lock. Like we have the result, and if old is still this valid thing, then we exchange it for old plus temp. Otherwise, old may have changed underneath us. So, but if the CAS finds that old has changed, then we don't update it. So it's not wrong. And we just come back around in this while loop. Yeah. So now what happens if we get swapped out on this loop iteration?
So in the while loop, the O will get updated every time.
Okay, right. No, old will be updated every time you come around. Like, old and new are just like these temporary variables.
Yeah.
And old will like, okay, so the first time around you said old equal to result and you said new equal to old plus 10. And then CAS, and so you have two cases on compare and swap. Either
The other hand.
the result has not changed out underneath you and you can just swap it out for new. The other case is the result has changed out from underneath you, but then then the CAS would find that old is no longer equal to result. Like you can think of compare and swap as like, you compare these two. And if true, then you swap new into result. And if false, then you just come back around. So if result has changed out from underneath you, then this comparison failed, and you have to come back around to here. And now old would be sent to the new result, which is whatever got changed out by another thread. Is that okay?
That's a two quick question. In the previous example, when we swapped out on a loop iteration, would we have a deadlock or would it just have to wait?
It's not exactly a deadlock in the sense that like, if eventually you get scheduled again, then
I see.
you'll finish. Like deadlock is, no matter what the thread scheduling is like, nobody can ever continue because there's some circular wait, like A wants B, B wants A, and then you
That
can't
makes
continue.
And then my second question is, so does this ensure correctness always? Because aren't there sometimes where you don't update the results in the for loop? If the cast is false?
Good question. So if like, if somebody, you're saying like, if this got changed out underneath you,
Yeah,
you want to come back around here.
oh, I see the do, I get
Yeah,
it.
this would return true if you did the, yeah, so if this returns true, then the tab was successful and you exit the do while.
I see,
If it returns false, it was unsuccessful, you come back around and you try again.
I see.
Good point. So this solves the issue that we had before, which is with the locks, if you get swapped out right after you take the lock, everybody has to wait. But now with CAS, no other loop iteration needs to wait. If some other iteration got scheduled, it can just keep going with this CAS. So it is non-blocking. Yeah. Does that make sense?
Quick question, just in the previous slide,
Yes. Anyway.
previous slide.
Oh, sorry. Yes. This one.
Yeah, in this algorithm, because it is running in different threads, but only one process, right?
Mhm.
So the operating system decides which process is running at a time. So if a process is asleep, then all of the threads would all sleep. So maybe other threads
Oh.
won't have to wait.
I see. You can have multiple processors.
Oh, yeah,
That's
that's
possible. That's a good point. If you, yeah, if they were all in one process, I guess nobody could continue. If you had more than one process, they still could not continue because one thread is holding the line.
The scheduling unit in operating system is RAM.
Yes. Like there can be more than one thread per processor. Yes. But yes, the threads get scheduled. Cool. So, are we okay with that? So in the last bit, I want to talk a little bit about lock-free algorithms. And basically, like I said, they're all pretty much built on CAS, but they are more complicated than some. Yeah. So let's do like a basic data structure, like a stack. So a stack, we have some node and we just push and pop the node onto the head. And yeah, so we have this, we have some values here. And this node has the structure. It's very simple. It has this next pointer and it has some data. And then the stack itself is just like a pointer to the head. And then you can traverse the stack just by following next. Okay, so we want to do, how would we do this lock-free push? You can use a similar trick to what we were just doing with the sum. So we have this do while, and instead of using it for like integers, it is still like an integer in a sense, but instead of doing it for like actual numbers, you can do it for pointers. Because a pointer is like it's like a 64-bit integer in a sense. So you want to push this node onto this on the front of the stack, and basically you want this to become the new head. You do the push. And the way it works is that you set node next equal to the head. So like here 92 is the current head, you're trying to push 81 on, and you set node next equal to 92. And this CAS, the X value is now a pointer, which is the pointer to the head. The old value is node next, which is what the previous head was. And the thing that you're trying to swap in is the current node that you're trying to push on. So if this CAS is successful, it means that nobody swapped out. So everybody is trying to, like, if you have multiple threads trying to push, everybody is trying to update head. And if the CAS succeeds, which means that the head is equal to node next, that means that nobody changed out the head from under you, and you are able to push yourself onto the stack. If the CAS fails, it means head, it means like this was what head just was, and it is no longer what is head currently. And so if this CAS fails, the do while has to come back around. And you have to update this again to what somebody changed at the head under you. Does that make sense? And yeah, so like I said, if you have multiple threads running, sometimes this CAS may fail if some other thread changes the head before you get to it. And so it comes back around. That's kind of, it's like the sum example, pretty much. Like if somebody updated the sum before you, then you cannot update the sum because it's out of date. So you have to read the new sum and add your contribution and then try to update it again. And it's like a similar idea. And so if you want to pop it, you set current, which is some temporary variable equal to head. Okay, yeah, you have current, and then you're trying to basically you're trying to set head equal to head next. And so you set current equal to head, and you're trying to swap. Yeah, you're trying to swap this head for head next. And so head, you do a CAS on this thing on current and current next. And while you still have elements, you check the head and you check it for equality with current, and this is head. And if these are equal, then you set the head to head next. And if they're not equal, it means somebody either pushed or popped something from under you. And then you have to update your view of what is the head of the data structure, and then you come back around. And then you just return it at the end. Yeah, so like this, and then you swing the pointer forward. Okay. As an optimization, so compare and swap is expensive because it has to acquire the cache line and then it invalidates the cache line and all the other caches. So you have to do the cache coherence protocol, and it causes some issues for performance if all processors are trying to do the CAS to the same cache line. And so a better way performance-wise is first do a read at some memory location to check if it changed, and only try to proceed with the write if the value doesn't change. And if you read it, it's not invalidated in the other caches because it's not taken in exclusive mode. So the way you would do that is you just add previously, it was just the CAS in the if statements, or out here in the while statements, but you just add a check. This is just a check that this first thing is doing, but you just hit it outside of the atomic operation instead.
Why don't we just think that current swap only validates the cache line? We are actually making.
Sorry?
Why don't we just make the compound swap only invalidates the cache line if we are actually making any changes?
It's a good question. Maybe it's hard to implement under the hood. Because if you take it in, well, how would you do that? Because if you do the check, oh, I see. Why don't you just build this into the compare and swap?
Yeah, exactly.
Maybe they do that. I actually, maybe this is old fashioned and actually haven't done recent benchmarking of compare and swap. You could, if you were trying to optimize compare and swap, this could be something that you just put in under the API. And so, I actually don't have recent benchmarks for compare and swap. Maybe they already do this.
Maybe they can put it in the file that if you call the compare swap.
Yeah.
It will just give you this instructions, or maybe they can do it on hardware level.
Yeah.
You call them. So routine, it will just download.
Yeah, I actually, they might, people will spend time optimizing compare and swap at the software level, just you just call it from the C library. So actually they might already do this. I'm not sure, but I can do some testing and well, actually I'm not sure, even if I did some testing, I'm not sure how that would tell me if they did it or not, because you can't see the implementation, but maybe you could do some testing about you just do some artificial testing to invalidate the cache line, and then you do this reading first, and you can check the comparative performance or something like that.
Like maybe compare swap variable and not a one other.
Mm.
Can we really gain something? Can we really gain any extra improvements by just writing another array?
If it is not already included in here, it may give you some improvement because you can short circuit if this comparison fails, and then you don't have to do any atomic operation. It may already be included, but I don't think that anybody who doesn't work on it can know that. Yeah, so, oh, I'm almost out of time, but to wrap up, we talked about stack in terms of lock-free. There are a lot of known classical data structures with lock-free variants like linked list, queue, skip list, hash tables, and they're basically all built on this like pointer compare and swap. And in theory, a thread might starve because like it may, like if the thread never completes its compare and swap, then it can never continue. But in practice, it rarely happens because usually you don't have like extremely high contention. And in terms of practical issues with lock-free data structures, memory management, there's contention, and then there's this ABA problem, which I don't really have time to get into because I'm out of time, but I have extra slides at the end that you can look through. At a high level, the issue is like, say you have two threads, and then the data structure is like, it has to do with like memory reclamation, basically. Like if you are thread one and you are trying to like, just take the stack example, like you're trying to push something onto the stack, and underneath you, like then you get scheduled out, and underneath you, somebody like pushes and pops a bunch of stuff that reclaims like the garbage memory, and then then thread one comes back around, and like your view still looks correct, but actually it is still actually is garbage because like somebody else modified the memory. That can happen. You can fix it with timestamps, but it's like it becomes uglier. So that is a correctness issue. And in terms of performance, I feel that locking data structures are still maybe more popular these days, but there are some cases where lock-free ones can be faster, and they are kind of elegant because I don't know, it's a nice application of compare and swap.
I think the only advantage where lock-free is faster, we discussed before, is that if we consider the operating system scheduling, then lock-free is faster.
Yes.
And in other cases, I think it's similar to log algorithms. Because log can be implemented by CAS.
Yes, exactly. Yeah. Though like the scheduling issue can happen also for data structures, like in the stack example, like you try to, if you were imagining like a lock-based stack, like you just stick a lock on the head, and if you grab the lock, you may get scheduled out, and then nobody can now push and pop. So if you have scheduling issues, or if you have high contention, they may cause issues.
There are other benefits we can gain from lock-free, in addition to better scheduling.
Are there other benefits of lock-free data structures? You don't have to, like in a linked list, for example, you have to put a mutex on every node. And then in the lock-free data structures, you don't need any extra space. If you really care about the mutex size, maybe you can save it, I guess. That's some benefit. It's not huge because the mutex is like, if it's just in exclusive mode, it's 1 bit. If it's reader-writer mode, it's like many, but I don't think I'm not sure, like the lock freedom does not immediately extend to reader-writer concurrency. So maybe there's a way to do it, but yeah. Maybe if you really cared about that. I think it's more of like a theoretical, elegant thing, but it is a nice trick. Yeah. Thank you.